regarding domain and asymptotes. And so if you're looking for the domain and the asymptotes of a rational function, and I've been stressing the degree of the divisor, but in this particular special case, you just want to mention something about the leading coefficients. Okay, and let's say if you have a function r of x, and we have is equal to 4x squared plus 10x plus 1, and say we'll have this to be all over 2x plus 1. Okay, and for this, and this is a different kind of divisor. Now, it is linear, and when we transition from log division to synthetic division, okay, our divisor was not only with x first order, but where the just the leading term was x without any coefficient other than 1 in front of it. But here we have 2x plus 1 as the divisor. And if I were looking for, let's say, the domain and the asymptotes, okay, now we have, for this setup, again, we have a rational function, and for a rational function to be defined, okay, so again, the denominator cannot be equal to 0. So you have, again, 2x plus 1 cannot be 0. And looking at finding out what the exclusion is going to be, first of all, if x is such that 2x plus 1 cannot be 0, then we have 2x cannot be equal to negative 1. And it's going to turn out that for the exclusion from the domain, we're going to end up with the restricted value at negative 1/2. So we have that x cannot be negative 1/2. Okay, and so for what we have in the case of the domain, okay, if x is going to be any value that belongs to the rational function, where the rational function is defined as a real number, either x is going to be less than negative 1/2, or it will be greater than negative 1/2. And for r of x, now this expression is already in simplified form. Okay, so meaning that you're not going to have the denominator factor to cancel. Okay, so this is going to signal that 2x plus 1 remains. And it's going to turn out that since 2x plus 1 remains, that the exclusion from the domain is going to be the vertical asymptote. So we're going to have a vertical asymptote at x is equal to negative 1/2. So we have at least one asymptote. Now in terms of any other asymptotes, okay, again, this will come down to the comparison of the degrees between the numerator and denominator. Okay, so we have r of x. Once again, we have equal to 4x squared plus 10x plus 1 and we have all over 2x plus 1 And for the degrees, okay, so in the numerator, okay, we have the degree is equal to 2. In the denominator, okay, again, stemming from x, which is a first order, we have that m is equal to 1. So we have that n is greater than m by 1 degree. And so this is going to signal that, okay, we're going to have a slant asymptote. All right. Gotcha. Okay, so you have, in the case of a slant asymptote, okay, now we have the divisor to be at 2x plus 1. And I'll give you just kind of a setup here. Okay, so so you have your slant asymptote. You have y is equal to, and now one way you can set this up, okay, say if I go with long division, okay, so I have 2x plus 1 into 4x squared plus 10x plus 1. Okay. All right. And I'm going to go with long division exclusively. And the reason for this, okay, we do have a linear expression, but I had that 2 in front of the x, so it creates a bit of an imbalance, which prevents me from going directly into synthetic division. But now if I had x plus 1, I have like -1, then 4, 10, and 1, and then do the column by column adding. But that 2 at the front, it prevents the synthetic division setup from becoming automatic. And so for what we have in the process, again, so we have for this rational function, again, we have -1/2 excluded from the domain, and again, since the rational function is already in simplest form, okay, the exclusion is the vertical asymptote. Now, again, we have a 1 degree difference between the numerator and denominator. And so there's going to be a slant asymptote, and we're going to have y equal to the quotient that results from taking 2x plus 1 into 4x squared plus 10x plus 1. So looking at what we have in the leadoff, okay, so we have 2x will go into 4x squared 2x times. Okay, so if I distribute, so we have 2x times 2x. Okay, so this will become 4x squared. And then I have, in the case of taking what we have for 2x distributed over 1. Okay, so we have distributing, so we have 2x times 1 is 2x. And then we have, in the case of distributing subtraction, okay, so we have 4x squares will go out, and then we have 10x minus 2x. Okay, so this will become 8x, and now I can bring down the 1. Okay, and then we have 2x, okay, went into 4x squared 2x times. Now we have 2x going to 8x 4 times. And distributing, okay, so you have 4 times 2x is 8x. And 4 over 1, okay, so this will become 4. And once again, taking the difference. Okay, so 8x will go out, and we have 1 minus 4, okay, so this will be -3. And again, so we're going to end up with the remainder at -3. And we have end result. Now I cannot take 2x into -3 because the degree this time we have x of first order, and -3 is not even an x term at all. So we have with the quotient at 2x plus 4. Okay, this will be that which will define the slant asymptote. So we have y is equal to 2x. Again, y is equal to 2x plus 4. And now, just to give you a little bit of a view, see we have from from Desmos. Okay, so we have, no, not looking at the calendar. Oh, good grief. Boom, 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 boom. Sorry, things get kind of twitchy. Okay, so we got, let me go ahead and, there we go. Okay, so if we go into Desmos, okay, so we have for this interaction, okay, so we have y is equal to, and we have 4x squared plus 10x plus 1, and we have divided by, okay, 2x plus 1. So just kind of zooming in, zooming out, okay, and we have, so this is the graph of this particular function. Now we had with the asymptote, okay, we said that we had that x is equal to -1/2. Okay, so if you notice, you have a vertical asymptote at x equal to -1/2, and at the extreme verticals, heading to positive as well as negative infinity, those sections from the rational function, okay, they will never come into contact. They'll get closer and closer and closer, running tangent in fashion, but they will never come into contact with the vertical asymptote. Now, as for what we have in the case of the slant asymptote, and that was y is equal to 2x plus 4, and we have, notice we have, let's kind of zoom again here, a little bit of a crisscross pattern. Okay, so we have at the extremes, and it's going to turn out for the slant asymptote. Okay, notice at the extreme left and the extreme right, can we have just to be running tangent in fashion as well. So this is what we're going to have for the graphing, okay, of the rational function 4x squared plus 10x plus 1 over 2x plus 1. And again, we have just as sort of the barriers, we had the vertical asymptote x equal to -1/2, as well as the slant asymptote, which we have again at y is equal to 2x plus 4. All right, now looking at what we have, going back to where we left off in the case of working with inequalities, and now for what we have in the case of polynomial inequalities, and now we'll just kind of take just as setup here, and we had looked at a table, okay, set up, okay, with regard to polynomial inequalities. And I was going to kind of put, I guess, sort of like 5 problems into one, but it's essentially, I'm going to kind of supply bricks and then just add the appropriate amount of mortar to kind of make things kind of join together well. And for what we have in the case of polynomial inequalities, and let's see for what we have here. let's say if I were to determine the values x, and we'll say that we have, okay, first of all, again, just kind of taking this as an example. Okay, say if I have, say we have x squared plus 6x is equal to 16. And I'll say that I have x squared plus 6x is less than 16. And I have x squared plus 6x is less than or equal to 16. And say that just reversing course. Okay, if I have x squared plus 6x is greater than 16, as well as x squared plus 6x is greater than or equal to 16. Okay, so you have these 5 problems, but you still have on the left-hand side, you have x squared plus 6x, and to the right, I have 16. Okay, first of all, on the side of the equation, okay, so we have, first of all, okay, so we have with x squared plus 6x is equal to 16. Okay, I have a quadratic equation, and this is not given in standard form since it is not set to 0. Okay, but I can make amends with this. Okay, so what I can do here, for x squared plus 6x equal to 16, I can just take 16 away from both sides. So I will have x squared plus 6x minus 16 is equal to 0. And here with the quadratic equation, okay, that is in standard form, I can factor the trinomial, whereupon I'm going to have the quantity of x plus 8 times that of x minus 2 is equal to 0. And so just looking at what we have with the zero product property, okay, so if I set each of the factors to 0, okay, so if I have x plus 8 equal to 0, okay, I have x equal to negative 8. And for x minus 2 equal to 0, so I have the x is equal to 2. So in the case of the solution for the equation, okay, so I have 2 values, okay, whereupon we're going to have negative 8 and positive 2. And I'm going to use these values to kind of set up a table. And so just kind of taking what we have now, so we got 0 values at negative 8 and 2. Okay, and what we'll do here is that as kind of a backdrop, okay, for solving these inequalities, okay, we set up a table that will be fixated about negative 8 and 2. And so just looking at what we have, okay, just setting up intervals. Okay, so between the zeros, okay, the smaller is at negative 8. And I'm going to work around the real number system. Okay, so we have at the extremes, okay, we have at the minimum, I have those values of x that will be less than negative 8. And bypassing negative 8, okay, so I have those values of x that will be between but not including negative 8 and 2. And then after this, okay, we have those values of x which will be greater than 2. So I'm establishing a set of open intervals. Okay, so I'm working around the real number system and setting up intervals that will not be inclusive of the zeros. Okay, so just kind of setting things up here. Okay, so we have, in terms of the rows and the columns formations. Okay, first of all, okay, now the other day we looked at test values. Okay, so just kind of taking what we have here. Okay, so if I were to go with an input value, like a test value x, okay, first of all, anything that is less than -8, we'll go with, say, -10. And then between -8 and 2, okay, 0 seems to be the most popular choice if it can be applied. Okay, and then anything greater than 2, we'll just go with the number 3. All right, now in terms of what we're going to use these values to test out, okay, notice whenever I rewrote this equation as a quadratic in standard form, okay, that which is set equal to 0 or compared to 0 is going to be our f of x. Just kind of going with this. Okay, so you have f of x. You have is equal to x squared plus 6x minus 16. Okay, and so testing out this function, in other words, you're looking at your y value, and then you have your input values x. Okay, so you have f of -10. We have f of 0, and also we have f of 3. Okay, so in terms of sign values, okay, so for f of -10, so I have the square of -10. Plus 6 times -10. We have minus 16, so square of -10 becomes 100. And we have minus 60. Minus 16. So we have 40 minus 16. So we're going to have for the outcome, okay, this is going to be a positive 24. Again, I'm stressing the signs here. Okay, now for f of 0. Okay, so you're going to have 0 squared. That is 0. We have plus 6 times 0. And we have minus 16. And you got 0 plus 0 minus 16. So we have for this output, okay, that is going to be negative 16. And for what we have in the case of f of 3, okay, so we have 3 squared. And we have plus 6 times 3 minus 16. So 3 squared is 9. 6 times 3 is 18. And we have minus 16. So 9 plus 18 is 27. And then take away 16. And so for that difference, okay, that is going to be 11. and it's sort of a backdrop to solving these inequalities. Okay, so just looking at the sign value of f of x. Okay, and notice, okay, when I tested out -10, the output was positive 24. And this is just a sample indicating that anything I plug in for x that is less than -8, the output is going to be positive. I plugged in -100 or -222, the output is still going to be positive. So in this case, we have that f of x is greater than 0. And anything that I plug in that is greater than -8 and less than 2, 0 being a sample, the output is going to be negative. So that means that as a comparison to 0, we have that f of x is less than 0. And then for anything I plug in for x that is greater than 2, like 3 being an example, okay, it turns out that the output is going to be positive. So just like anything that is plugged in less than -8, we will have for those values x plugged in that will be greater than 2, the output is going to be, once again, positive. Okay, so for what we have in the scheme of things, okay, so we had worked out x squared plus 6x is equal to 16, and reworking as a quadratic equation in standard form, I had these zeros to come about, and for what we have for the respective inequality statements. Okay, so for what I have in these inequality statements, so if I rewrote each of these as a comparison to 0, so I would have x squared plus 6x minus 16 is less than 0. Then I have x squared plus 6x minus 16, okay, is less than or equal to 0. And then just moving 16, we have for this inequality, I would have x squared plus 6x minus 16 is greater than 0. And then in the rewrite for the last of these inequalities, so I have x squared plus 6x minus 16 is greater than or equal to 0. Okay, and again, we had x squared plus 6x minus 16 to refer to f of x. So in looking for the solution set, okay, so for what is going to abound, okay, so for this statement less than 0, this is going to reference f of x is less than 0. Then we have f of x is less than or equal to 0. And we have f of x is greater than 0. And then for the last inequality, okay, again, we translated to a comparison to 0 statement, and so the last case, this would be where f of x is greater than or equal to 0. Okay, so for what we have in each of these, okay, we're going to have for the solutions, okay, notice we have f of x is less than 0. So in terms of interval notation, there will be no brackets, just parentheses. So where x squared plus 6x is less than 16, again, as a comparison to 0, we have x squared plus 6x minus 16 is less than 0. And just from the table, this will refer to f of x is less than 0. So where is this going to happen? Well, if you look at the top row, okay, and we have with the column heading, we have -8 and 2 enclosed in parentheses. And now where we have f of x is less than or equal to 0. Now direction-wise, you're going to have the values, okay, in the same direction as where we had less than 0. So you're still involving the same limits, -8 and 2. But since the inequality has the equal sign, well, guess what? -8 and 2 create the equal to 0 part for this function. And since -8 and 2, thanks to the equal sign, are going to be included, we have brackets wrapped around these values. And for where we have for the greater than and the greater than or equal to statements, and again we have just for the spread, okay, so for x squared plus 6x is greater than 16, again we have this as a comparison to 0 inequality. And for the solution, this will make reference to where we have f of x is greater than 0. So where it is greater than 0, we have this set of values. Okay, so you have those values of x less than -8. And also we have f of x is greater than 0 for those values of x that will be greater than 2. And for where we have greater than or equal to, we're looking at the same numbers, but where -8 and 2 will be included. Okay, so you have those values of x less than or equal to -8. So -8 is going to be in the bracket. And also we have those values of x that will be greater than or equal to 2. Okay. So you're going to have less than or equal to inequalities to almost be identical, but where we have the equal sign, you're going to wrap brackets around those values that cause the polynomial to be equal to 0. And the same thing could be said for the greater than as well as the greater than or equal to statements. So those are going to be your respective solutions for what we have in the various equation and inequality combination. And now, just looking at what we have, say just looking for the solution of one particular inequality. And I tell you what, let's say just for the next few moments, okay, tell you what, let's see what we get for so in this case, say we're looking at determining the solution of x squared minus 4x is greater than or equal to 32. Okay, for what we have for this inequality, so we have just x squared minus 4x is greater than or equal to 32. And so for setting things up, okay, now we need to determine, okay, just what zeros, okay, we're going to have for this expression. Okay, so we have in the process, okay, so we're looking at determining, the solution of x squared minus 4x is greater than or equal to 32. Okay, so just kind of setting things up and finding out just what values of x we're going to be working around in the table setup. Okay, so if I have x squared, say first of all minus 4x is equal to 32, and I rewrite this in standard form. So I'm going to have x squared minus 4x minus 32 is equal to 0. And just looking at factoring. Okay, so we have, looks like we have more weight given to the subtraction than to the addition. Okay, so I have x plus 4 is equal to 0, and x minus 8 equal to 0. And if x plus 4 is equal to 0, so I have that x is equal to negative 4. And if we have x minus 8 equal to 0, so I have that x is equal to 8. Okay, so just in terms of setting things up in the table, okay, we have just in the respective rewrites. Okay, so we have the f of x is equal to x squared minus 4x minus 32. Again, for the solutions in x, okay, those are going to be the zeros. So we have negative 4 and positive 8. Okay. And just setting up a table with intervals. Okay, so you have the zeros at negative 4 and 8, and negative 4 is the smaller of the zeros. And so we're going to have, starting out with working around negative 4, so we have at the lower end, we have those values of x less than negative 4. And then bypassing negative 4, and then we'll go with those values of x that will be higher than negative 4 and less than 8. So now we're working around 8. So going from greater than 8, then bypassing, and for the rest of the subintervals, we'll have those values of x which will be greater than 8. And so we have, in the case of setting up a table, and dividing the subintervals into separate column headings. Okay, so just in the realm, okay, of testing out each of the sections through the application of tested values. Okay, so in case of the test value x, okay, so if I were to test out any value that is less than negative 4, okay, we'll go with, let's say, negative 5. And anything greater than negative 4 and less than 8, I can go with 0 again. And then we have anything greater than 8, well, I can just go with, say, the number 9. And again, we had with our function to test out again, so we have f of x. Again, we have equal to x squared minus 4x minus 32. And so just testing out what we have for f of negative 5, as well as f of 0 and f of 9. Okay, so we have with f of negative 5. Okay, so we have the square of negative 5. And we have minus 4 times negative 5 minus 32. Okay, so the square of negative 5 is going to be positive 25. Negative 4 times negative 5 is going to be a positive 20. And we have minus 32 to follow. Okay, so you have 45 minus 32. And so we have that difference on the plus side at 13. Okay. And then we have for the next item, okay, so we have for f of 0. Okay, so we have, so you got 0 squared minus 4 times 0 minus 32. Okay, and so that is going to go to negative 32. And we have for f of 9. Okay, so it's kind of working through this. Okay, so you have 9 squared minus 4 times 9. And we have minus 32. And so we're going to have 9 squared. Okay, so that's going to be 81. Then 4 times 9, you have subtraction of 36. And we have minus 32. And we have, once again, 45 minus 32. And so that is going to come out to positive 13 as well. Okay. And so we have just looking at what is present. Okay, and we have for the sine of f of x. Okay. So when we test out negative 5 as an input that is less than negative 4, okay, this signals that anything we plug in less than negative 4 for x, your output y is equal to f of x is going to be positive. So here you're going to have the f of x is greater than 0. And anything between but not including negative 4 and 8 as the input, the output is going to be a negative. So you'll have the f of x is less than 0, and then any value you select for the input, okay, that is higher than 8, the output is going to be a positive value. Okay, so you're going to have the f of x, once again, is going to be greater than 0. Okay. So just looking at what we have, just packaging everything in. And so we have with x squared minus 4x is greater than or equal to 32. And again, just translating this out as a comparison to zero inequality. So I would have x squared minus 4x minus 32 is greater than or equal to 0. Or in this case, so this would be another way of saying that we have f of x is greater than or equal to 0. And so for what we will have in the case of the solution, in this one, okay, so for f of x is greater than or equal to 0, again, you'll be going in the same direction as f of x is greater than 0. So I'm just going to kind of denote this. Okay, so for f of x is greater than or equal to 0. Now for the limits in the solution, okay, so we're looking at the first and the last subinterval sections. So we're involving negative infinity and negative 4. And also where f of x is greater than 0, we have 8, and we have going out to infinity. Now since the nature of the inequality includes the equal sign, okay, we might have brackets and parentheses in the mix. So now for infinities, negative and positive, these are boundless. So those will stay in parentheses. And since negative 4 and 8 cause x squared minus 4x minus 32 to equal 0, and since negative 4 and 8 set this trinomial to 0, that means that negative 4 and 8 are included. And that is thanks to the equal sign in the statement. And so you're going to have brackets around these particular values. Okay, and so that is going to be your interval solution for what we have for this particular inequality statement. And now, just a couple of cases here. And say if you're looking for interval solutions, okay, I was saying this, okay, we'll start out with just comparison to 0 inequality. Now say we have x squared minus 6x is less than 0. Okay. And again, just looking at the zeros from this. Okay, so if I were to form a table, okay, around the zeros, so like if I had x squared minus 6x equal to 0, right, so we have already in the setup the standard form. So I can go ahead and factor. So we have x times the quantity of x minus 6 is equal to 0. And from x, I have x equal to 0. And from x minus 6 equal to 0, I have the x's equal to 6. Okay, so already as a comparison to 0, okay, I have, again, that already setting up the zeros. Okay, so I have f of x is equal to x squared minus 6x. And again, we have with the zeros. Okay, so you have x at 0 as well as x at 6. And just for the interval setup, okay, so I have from negative infinity approaching, but not including the smaller of the zeros. In this case, I have it 0. Then have going past 0 approaching, but not including 6. And then we have for the rest, okay, have those values of x which will be greater than 6. And again, just setting up our table. And then assigning test values. Okay, so this is where we are heading out. Okay, so we're looking at assigning test values for the input. And then you're looking at testing out f of x, which I have at x squared minus 6x. Then I have the sign of f of x portion. So you have test value as in tested value for x. Okay. So for the first part, okay, so anything less than 0, okay, it's going to be a negative value. So I could go with, let's say -2. Then anything between 0 and 6, again, I could choose 1, 2, 3, 4, 5 among the natural numbers. I'll just go with 3. And then anything greater than 6, I'll just go with the number 7. Okay, so looking at what we have and testing out f of x using the respective inputs. Okay, so we have with f of -2. Okay, so we're going to have the square of -2 minus 6 times -2. And so we're going to have -2 squared is going to be 4. -6 times -2 is going to be a positive 12. And so we're going to have for this output, okay, so that is going to be a positive 16. Okay, we have for f of 3, okay, so you have 3 squared minus 6 times 3. 3 squared is 9. -6 times 3 is -18. And 9 minus 18 becomes -9. And then for f of 7, okay, so you have 7 squared minus 6 times 7. 7 squared is 49. -6 times 7 is -42. And 49 minus 42 is going to be a positive difference. That's 7. Okay, so for the sign of f of x, so anything I plug in less than 0 is going to result as a positive value. So here I'm going to have that f of x is greater than 0. Anything I plug in greater than 0 and less than 6 is going to result as a negative output. So I'm going to have that f of x is less than 0, and then anything I plug in higher than 6 for x, the output is always going to be positive for that particular function. So I have that f of x is greater than 0. Okay. And now, so just looking at what we have for the inequality. So I have x squared minus 6x is less than 0. And this is already established as a comparison to 0 inequality. So x squared minus 6x is less than 0. So this is going to reference where we have f of x to be less than 0. And just looking at what we have referencing from the table. So we're going to have for the interval solution. Okay, so we have f of x is less than 0, so looking at the column heading, and so it'll be exclusively those values of x such that 0 is less than x is less than 6. Okay, so that would be the outcome for this one. Now, and let's say that if I have an inequality, say if I have x squared minus 3x is greater than or equal to 18. Okay. So I have x squared minus 3x is greater than or equal to 18. And what I can do is that if I were to rewrite this as a comparison to 0 inequality, Okay, so I would have x squared minus 3x minus 18 is greater than or equal to 0. And let's say that if we determine just what the zeros will be. Okay, so for x squared minus 3x equal to 18, if I take 18 away, again, so you have x squared minus 3x minus 18 is equal to 0. And we have in factoring. So we have the quantity of x plus 3 times that of x minus 6 is equal to 0. Okay. So for the values of interest, okay, we're going to have at -3 and positive 6. Okay, so just kind of taking what we have here. Okay, so you have f of x equal to x squared minus 3x minus 18 . And for the zeros, okay, so you have a -3 and positive 6. And in the case of setting up intervals, okay, so you have -3 and 6. Okay, so you have working around the real number system, so we'll start out with those values of x less than -3. Then we have those values greater than -3 and less than 6. And then we have those values of x which will be greater than 6. And again, setting up a table. Okay, so you have the intervals as the column headings. So we have the process. Okay, so we're going to test each of the sub-intervals with an input value that is going to belong to each of the referred to interval sections above. So you got your test value x. And again, we're going to apply to the function f of x is equal to x squared minus 3x minus 18 . And then you'll be looking for the sign value of f of x. Okay, so for the first tested value, we can select anything that is less than -3. So it's going to be a value that is more highly negative than -3. Okay, and so we can go with, we'll say -5. Okay, so if I test out -5, so for f of x, we have f of -5. So just replacing x with -5. So we have -5 squared minus 3 times negative 5 minus 18. So you have negative 5 squared is 25. Negative 3 times negative 5 is going to be 15. We have minus 18. So 25 plus 15 is 40. Take away 18. So we have, for this result, okay, that's going to be on the positive side at 22. And then if I were to test out any input that is greater than negative 3 and less than 6, we can once again go with 0. And guess what? If I plug in 0, you got 0 minus 18. So here the output is negative 18. And then for anything that is greater than 6, we can go with the number 7. So you have f is 7, so you have 7 squared minus 3 times 7 minus 18. 7 squared is 49. You got minus 21 minus 18. 49 minus 21 is 28. Take away 18, and the difference is going to be positive 10. Okay, so looking at the resulting outputs, so for the sign of f of x, first case, okay, this is going to be positive, so you're going to have the f of x is greater than 0, and then from the middle, we're going to have a negative output. So we have the f of x is less than 0, and then we have for any value input that is greater than 7, the output is going to be positive. And so for what we're going to have in the overall picture, okay, so we started out at x squared minus 3x is greater than or equal to 18. And again, rewriting this as a comparison to 0 inequality once again. So I have x squared minus 3x minus 18 is greater than or equal to 0. And again, we have f of x is this trinomial. So you're looking at whereupon f of x is greater than or equal to 0. And so we're going to have for the solution, again, greater than or equal to 0 is in the same direction as greater than 0. So looking at where, at least on the side where f of x is greater than 0, so we are applying the first and the last subintervals. Okay, so we're involving the limits negative infinity and negative 3. And also where f of x is greater than 0, so we're involving 6 and infinity. All right. And in terms of the enclosures, now infinities are boundless. So you have a parenthesis around negative infinity as well as around positive infinity. And with an equal sign, this opens up the possibility of brackets once again in the mix. And negative 3 sets the function equal to 0. So negative 3 is part of the solution. And 6 likewise causes the function to be equal to 0. So that is included. And so 6 is also going to be in the bracket. So this will be your interval solution for this particular inequality statement. And tell you what, just for the inequality, and so let's see what we get for so you have the solution or interval solution to, and we'll say that we have x squared minus 2x is less than or equal to 3. Okay. If you're still working on this, that's fine. But just going ahead and looking at what we have here. So we have x squared minus 2x is less than or equal to 3. And if I rewrite this as a comparison to 0 inequality, so I have x squared minus 2x minus 3 is less than or equal to 0. And to set up the table once again, I just need to go ahead and find out what in x would make x squared minus 2x equal to 3. So we have another quadratic equation. And if I write in standard form, so we have x squared minus 2x minus 3 is equal to 0. And we have with factoring, so we'll have once again more weight given to the subtraction than to the addition. So we have that x plus 1 is equal to 0. Okay, we have that x is equal to negative 1. And if x minus 3 is equal to 0, then we'll have that x is equal to 3. So just for what we have in terms of the function, so your f of x, that is, okay, that which we have compared to 0 in the rewrite. Okay, so you have x squared minus 2x minus 3. And for what we have in the case of the zeros, okay, so you have negative 1 and positive 3. And just setting up the intervals. Okay, so you got your zeros at negative 1 and 3. Negative 1 is the smaller zero, so the first interval we have between negative infinity and negative 1. Then we have between negative 1 and 3. And with 3 as the second and last zero, we have set of values x, okay, that will be greater than 3. Now for test value x, so anything less than negative 1, we can go with negative 2. Between negative 1 and 3, we can go with 0. Anything greater than 3, okay, we'll just go with 4. And for f of x equal to x squared minus 2x minus 3. Okay, so we're looking at, once again, we have f of negative 2, f of 0, as well as f of 4. So for f of negative 2, okay, so we're going to have in the setup, so we're going to have the square of negative 2 minus 2 times negative 2 minus 3. So we're going to have 4 from the square of negative 2. Negative 2 times negative 2 is a positive 4. And you have minus 3. So for this output, okay, so that is going to be a positive 8. And for f of 0, we got 0 minus 0 minus 3. So f of 0 is equal to negative 3. And for what we have in the case of f of 4, so we have 4 squared minus 2 times 4 minus 3. 4 squared is 16. Then we have minus 8. It's going to be 8 minus 3. Okay, so that output is going to be on the plus side at 5. Okay. And so for what we have in the mix, okay, all right, so we got for these numbers, okay, so for the sign of f of x. So anything we plug in less than -1, the output is going to be positive. So f of x is going to be greater than 0. Anything I plug in between -1 and 3, you're going to have a negative output. So f of x is less than 0, and then anything we plug in greater than 3, such as 4, okay, the output is going to be positive. So again, we're going to have the f of x is greater than 0, okay, and so for what we're going to have in this particular case, all right, so we got okay, so we got positive, negative, positive, and so we have with the inequality. So again, we had x squared minus 2x is less than or equal to 3. Okay, just in the rewrite, so we have x squared minus 2x minus 3 is less than or equal to 0. And so this is just going to be referencing again where f of x is less than or equal to 0. And so we're going to have, in the case of the interval solution, so you got the same direction as less than 0, so we're referencing the numbers -1 and 3. Now both -1 and 3 cause the equal to 0 part of regarding f of x to be created, and since we have the equal sign in the inequality, -1 and 3 are going to be included, and around those values will be brackets, and so that will be the solution to what we have here.